To find a few specific molecules hidden inside a massive, complex liquid, modern electroanalysis pushes detection limits down to the nanomolar scale. We are looking for trace elements suspended in an ocean of noise. The field relies on three primary pillars of measurement. On the left, potentiometry measures voltage differences while strictly drawing zero current. In the center, coulombmetry takes the opposite route, relying on exhaustive electrolysis to completely consume the target analyte over time. The third pillar introduces a different mechanism, controlled potential voltametry. Instead of destroying the bulk sample, this technique actively alters the cell's potential while recording the current. As this lower callout highlights, the reaction consumes only a tiny, negligible fraction of the analyte. Because this interaction is restricted strictly to a two-dimensional boundary, the surface of the working electrode, we cannot rely on bulk solution dynamics. Measuring data at this microscopic border requires exact hardware precision. To understand how this works, we must look at the physical hardware built to control the reaction, the physical chemistry that governs the interface, and the specific graphical shapes the instrument outputs. Voltametry operates as an engineered system designed to extract hidden thermodynamic data from a chaotic liquid environment. Start with a basic two-electrode circuit. When current flows through any solution, the liquid itself acts as a resistor. As the current pushes through, the applied voltage readout actively fluctuates. This fluctuation is the IR drop. Because the voltage is shifting based on the liquid's internal resistance, we lose the strict control required to target specific molecular reactions. To bypass this resistance, electroanalysis relies on the three-electrode cell. This diagram outlines the complete anatomy of the hardware. In this configuration, the physical current is forced into a closed loop. The orange arrows show that current flows strictly between the working electrode and the auxiliary or counter electrode. This closed loop allows us to introduce the critical third component, the reference electrode, which maintains a constant invariant potential baseline. The text box on the right explains the exact mechanism. By isolating the reference electrode so it draws virtually zero current, it completely evades the IR drop. The three-electrode cell ensures that the exact voltage programmed into the instrument matches the exact voltage the molecule experiences at the interface. Even with perfect voltage control, the electrical signal we actually report, the Faradaic current, is dictated by the physical processes happening at the electrode surface. The net rate of the entire reaction is strictly limited by the most sluggish physical process. The primary limitation is usually a contest between Step 1, mass transport, moving reactants to the surface, and Step 2, electron transfer across the interface. To calculate accurate concentrations, we must remove unpredictable movement from the equation. This diagram outlines the three ways molecules travel: diffusion, migration, and convection. The analytical takeaway box details how we restrict this movement. We add supporting electrolytes to suppress electrical migration, and we keep the solution completely unstirred to eliminate physical convection. This intentional suppression leads to fusion, the spontaneous movement of particles down a concentration gradient, as the strictly controlled bottleneck. By engineering the physics so the bottleneck is purely diffusion-controlled, the current we measure becomes a direct mathematical reflection of the analyte's concentration. With diffusion isolated, we dynamically sweep the voltage applied to the working electrode using cyclic voltametry. The instrument applies a specific input, shown here. The triangular waveform sweeps voltage forward to force oxidation, then reverses to force reduction. This input generates the output voltammogram shown on the right, characterized by its distinct asymmetrical duck shape. If we map them together, as the tracking line hits the apex on the left, the peak of the input triangle perfectly corresponds to the far right switching potential on the output curve. As applied voltage ramps up, the reaction rate accelerates. Molecules at the surface oxidize rapidly, pulling more current and creating the initial sharp upward slope. But the current suddenly drops off to form the peak because the reactant immediately touching the electrode has been completely exhausted. This creates a depletion layer. Because diffusion is our strict bottleneck, fresh molecules must now travel from deeper within the bulk solution to reach the electrode, causing the rate of current to decay. When the voltage sweep reverses, the instrument takes the newly formed oxidized product and forces it to reduce, generating the inverted cathodic peak. The duck shape is a real-time map plotting a diffusion layer as it expands and collapses. This specific shape assumes a fully reversible electrochemical reaction, where the actual electron transfer at the interface happens nearly instantaneously. This chart lays out the mathematical criteria for reversibility. Look at box 1. The voltage distance separating the peaks remains constant at 59 divided by n millivolts. Moving to box 2, the forward peak amplitude perfectly matches the reverse peak. But molecules often resist this change. When the internal chemistry makes the quantum leap of electron transfer slower than mass transport, the timing breaks down. This condition is known as sluggish kinetics. It pulls the system away from a reversible state and distorts the voltammograms shown here. The text box outlines the consequence. The instrument must supply extra voltage, an overpotential, to actively force electrons across the boundary. This extra voltage requirement physically stretches the data, pushing the anodic and cathodic peaks further apart along the horizontal axis, widening the gap well past the ideal 59 millivolts. Measuring peak separation provides a direct diagnostic of the target molecule's intrinsic kinetic speed. Deviations from the mathematical ideal give us the precise data needed to probe the reality of molecular behavior. Moving out of the pristine laboratory, these exact electrochemical principles are deployed to analyze complex, heavily confounding environmental matrices. This document highlights the analytical challenge, identifying trace pollutants, like heavy metals and pesticides, buried inside chaotic samples. We detect these by targeting specific chemical vulnerabilities. At the bottom, structures like biphenox contain highly active NO2 groups that are exceptionally responsive to targeted voltametric sweeps. To operationalize pure theory for field use, operators rely on highly adaptable hardware, specifically carbon paste electrodes. The key engineering advantage is detailed here on the left. The electrode surface is easily renewed by mechanical polishing, preventing permanent fouling from dirty field samples. The entire process relies on layers of precise control, isolating the interface with a 3-electrode cell, mathematically forcing diffusion, and decoding the resulting kinetic overpotentials to identify targets. This architecture transforms the electrode into a precision probe, using controlled voltage to isolate and quantify the behavior of individual molecules at the boundary of a solution.